Chapter 7, Problem 33, we have a block on a horizontal frictionless force that's attached to a spring with spring constant of 50 newtons per meter. The spring is relaxed. The block is stationary at x equals 0. Now we want to apply a 3 Newton force to the block that's going to pull it in the positive x direction and stretch the spring until the block stops. When the stopping point is reached, A, what is the position of the block, and B, what work has been done on the block by the applied force, and C, what work has been done on the block by the spring force. Okay, we kind of have to answer all three of these at one time, right? Because what we're looking for is at what point does the block come to a stop. What's going to happen is we're going to be pulling on the block, and it's going to pick up some velocity. And we're going to hit a point, right? We're going to hit a point where the block, where the force of the spring exceeds, right? And call it the force of the spring, becomes greater than the 3 newtons or greater than minus 3 newtons. And so the force, total force, starts being back that way, but the block is going to keep going for a bit until it decelerates and hits 0, right? So we got to work out all of these different pieces. So first, what is the work done on the block by the 3 Newton force? Well, that's simple and straightforward. The work done on the block by the 3 Newton force is just 3 newtons times x, the distance that it gets displaced. And I'm going to put this as by the applied force. Okay, so the work done by the applied force is 3 newtons times x. What's the work done by the spring? Spring has just the work done by the spring. Well, that's where we go back to our handy little int, and we're going to integrate from 0 to x, right? And the spring force is minus kx dx. Okay, so that ends up being minus 1/2 kx squared is the work done by the spring, or in this case, with the 50 newtons per meter, the work done by the spring is minus 50 newtons per meter, not 50, minus 25 because of the half, minus 25 newtons per meter times x squared. And what condition do we need to have met? Right? We've got the work done by the applied force, we got the work done by the spring, which is negative, and what we want is the two of these to end up summing to 0, right? Because if it starts off at rest, once we get to the point where all of the work done on it adds up to 0, it is again at rest, and we've met the condition that we're after for part A of the question. When, at what point does the block come to rest? And so adding these all together, we got minus 25 newtons per meter x squared plus 3 newtons x equals 0. Okay, so right away there's one solution, which is x equals 0, but that's a trivial solution because that's where we started. And the other solution is minus 25 newtons per meter x. I'm going to drop the units for now because we know x is in meters, and we do all of our units right. Minus 25x plus 3 equals 0. And so that gives us x equals 3 divided by 25 is the point at which, and that's meters, the point at which this comes to a stop, and this is 0.12 meters. So it comes to a stop at 0.12 meters. Part B. How much work was done by the applied force? Right? So work done by the applied force equals 3 newtons times 0.12 meters equals 0.36 joules. Part C. Work done by the spring. Well, the work done by the spring is minus 25 newtons per meter times 0.12 meters squared, right? equals minus 25 times 0.12 squared is minus 0.36 newtons, joules, sorry, which is exactly what we were hoping for since we said these added to 0. Okay, during the block's displacement, part D, what are the block's position when its kinetic energy is maximum and the value of the maximum kinetic energy? So, in part D, since we know that the kinetic energy is simply equal to the work that's been done on the block, right? And that in our equation right up here, those added up right here, right? There we go. This is the kinetic energy at any position x. And we want to know what the maximum kinetic energy is. Well, we find the maximum kinetic energy by taking dk dx, which in this case is minus 50 newtons per meter times x plus 3 newtons, okay, is dk tx, and we set this equal to 0. And what we find is that when x equals 3 divided by 50 meters, our x equals 0.06 meters, that the kinetic energy has reached its maximum. This is also the point at which the total force on it is 0. That we reach a point where there's no longer a positive force in the x direction because that's being completely canceled out by the spring. Past this point, it's decelerating. All right, so this is where, and what is that value? Okay, so what is that maximum value? So we know where is 0.06 meters, and so now we go back and we stick that into our equation for kinetic energy, minus 25 newtons per meter times 0.06 meters squared plus 3 newtons times 0.06 meters, right? So minus 25 times 0.06 squared plus 3 times 0.06, and we get 0.27 joules. 0.27 joules is the maximum kinetic energy of the block, and I believe that's the end of the problem.